Hello everyone, my name is Rafi Ibn Sultan and today I'm going to present our paper GeoSAM Fine-Tuning SAM with Multimodal Prompts for Mobile Infrastructure Segmentation. So let's get us started. At first, I want to thank ECAI and Wayne State University for giving us opportunity to present our paper in this year's ECAI 2025. This paper was presented by Professor Dongsha Zhu, the supervisor of our lab. If you have time, please check our lab. And we have all the links here, like paper link and code link. You can just go and check. So let's get started. So at first, the background. Uh, so we are actually trying to going for the mobility infrastructure segmentation, like the current mobility infrastructure segmentation in aerial imagery or let's say satellite imagery are all primarily on roads and not pedestrian structures. And most systems are designed to assist drivers, not pedestrians. And most of the traditional models depend on large volumes of manual level data for the models to make a good prediction. And they also suffer from data set variation and limited generalization. Like if you move your we have a data distribution shift, the model doesn't perform that good. So this kind of specific data are often are characterized by like scarcity of high quality annotations from human and also the variation across geographic regions. So the motivation we have, as I said, like the current models need extensive data, the traditional models also, it does not perform that good. Like it fails to segment sidewalks, crosswalk, which are really narrow in shape and very close to the roads itself. So then we have our foundation model, like the vision foundation model, which are already like it's a promptable vision foundation model. Let's say example is a segment anything model, the SAM, which is like already pre-trained on a large scale natural images, which is also task agnostic, like it can be converted to any task with easily adaptable with user provided prompts. And it demonstrated strong generalization, like but still struggles with spatially extensive structures like long sidewalks in an aerial from the bird eye view of an aerial image or satellite image. So let's see our proposed solution. So what we do is the goal of our this research work is to adapt SAM segmentation capabilities for mobility infrastructure imagery. The approach we do is that we apply lightweight fine-tuning on limited data, learn domain-specific patterns while maintaining adaptability across regions. Our framework GeoSAM is an end-to-end system, so it integrates geo-point generation, like the promptable, as we're saying, like it's a promptable foundation model. So the points are automatically generated, and it we have another semantic guidance, like a text prompts to reduce ambiguity from the points. Okay, let's see the architecture overview. So let's say we have an input image, which is an aerial image or satellite image, which goes into the foundation model. At first, it goes in the image encoder, gives us image embeddings. Then it also goes into this GPZ, which are calling the geopoint generation, which generates some points, like automated points, goes into the prompt encoder, gives us the point embeddings. And we have another text prompts, like let us say the user, whatever the classes that we are trying to segment, the user asks GPT, like, can you describe roads or sidewalks? Then GPT gives us some a small description of what road is, sidewalk is. Then it goes into text encoder, typically a normal text encoder like a clip encoder, and gives us text embeddings. Then this point embeddings and text embeddings are concatenated, which makes us gives us the prompt embedding that goes into the mask decoder, and with cross attention and self attention between the prompt embeddings and image embeddings, we get our predicted mask. So among this whole thing, this is our main three components of the foundation model of SAM, which we only train the mask decoder itself. So how the geopoint generation works, so like if we get an input image, we use another traditional model, like a pre-trained traditional model in the same domain, and we get some pseudo mask, let's say there are pseudo mask for each of the class, and we use the foreground information, like the foreground the mask has generated as like a possibility of points coming from. So we use points from those foreground pixels as like those points work as like clicks or points on the image. Like say you can see this is the road, so we have yellow points, or the other thing, the red points are the background points. So this helps the model to segment the road. Same thing happens for sidewalk or crosswalk. Like we have two sets of prompts. The first prompts coming from the foreground pixels, which are the positive clicks, and the background or the negative clicks work as to help Sam to focus on where to look and where not to look. The foreground points are for where to look, and the background points are for where not to look. Okay. The prompt generation, the first of all, the point prompts, like the primary cues for segmentation, as we see, it gives us the direction of SAM to look for, and automatically extracted from the pseudo marks, as we seen in the last image. Where to look, foreground prompts, background prompts, where not to look. The text prompts, it's like a semantic guidance. Like say, for example, some of the points can be overlapping, like a sidewalk, no, let's say crosswalk and road can be overlapping of a same pixel. So these text prompts will give us like semantic guidance on what we're trying to say. Like if it's a crosswalk we're trying to segment, then the model will know like it's a crosswalk that we're trying to segment. So the dataset we use, uh, it's from publicly available high resolution ortho rectified aerial imagery and publicly available GIS data. So based on that, we have three different splits of data. The pre-train, which is from Washington, D.C., and also D-test, also from Washington, D.C. So this train and test are from different regions of Washington, D.C., and we stitch them to make like we stitch images to have like a high resolution image, which we are dealing with. And we have another generalizability test, which is coming from Cambridge, which is much different than Washington, D.C., which we test our model, like how good our model is in generalizability test. So the training and testing performed and this D-train and D-test, and the DGen we do the additional evaluation. Here are some examples of this dataset. You can see these are the Washington and these are the Cambridge dataset. So for the experiment setup, we have like we use pre-trained weights of SAM, VIT. Most of them are frozen. The trainable is mask decoder. We use loss function for dice focal loss. Some typical optimizer for the point prompt, we use NN unit for like using the traditional model to generate the automatic prompts. And for text encoder, we use Clips VITB. And for prompts, we use 2000 foreground points and 1000 background points. So it's like a lot, but we'll see like a short while like why it's needed. So the source code is available in this GitHub repository. You can go and check it out. Okay, the post-processing, we do also some post-processing, like we use some morphological operations so the segmented maps are not like broken or there's like not anything like noise. So we remove those as well. And we have the results here. So we compare against other foundation model which approach, CNN-based model approach, and also transformer-based model approach. And for all the cases, we perform much better in both IOU and AP in both the test dataset and the generation dataset. Here's some visualization. The input image ground truth, GeoSAM, and also zero shot SAM. We show that the zero shot SAM, like without any training, the SAM does not perform well, and we show that why it needs further fine tuning. And against some other models as well. In most cases, we have much better detailed performance. So more results, we have like say, why do we use different prompts? Because let's we use the 2000 1000 automated prompts as our default settings because it gives us the best performance. And why it does gives us the best performance? Because sidewalks are typically like long spatially structured. So we need to cover everything before, otherwise the model gets confused between other closely related class. Sub-ablation study, like we show that why each of the modules that we use are very important. As we can see that the performance drops when we remove one of the modules. And some ablation study, like backbone ablation study, we show that our like instead of NN unit as a traditional one, if we use unit or swing unit, we still perform really good. And we have some model inference time analysis and parameter, etc. So thank you for listening. Hope you guys enjoyed it. So please visit our lab if you have interest in our current work. We do many computer vision and NLP related tasks. So that's basically our work, GeoSAM, which effectively adapts SAM to geography image and which also demonstrate generalization and structural accuracy. Hope you guys enjoyed it. Thank you again. Hope to see you soon.